Right now, inside a Pentagon research agency, 18 of the world's most advanced quantum computing companies are being put through a test most people have never heard of. The question they're trying to answer is quantum computing actually real, or is it the biggest bet in modern science history? The answer could arrive by 2033, and it could change everything. For decades, quantum computing has lived in a strange gray zone. It has been called the future of medicine, the future of materials science, the future of cryptography, and the future of artificial intelligence, all at once. It has also been called a mirage, a marketing story, a technology that always seems to be 20 years away no matter what year you ask. Billions of dollars have poured into it. Nobel Prizes have been awarded around it. Entire companies have gone public on the promise of it. And yet, until very recently, almost nobody outside the field could tell you whether any of it actually worked at a scale that mattered. That is, the gap. The Defense Advanced Research Projects Agency, better known as DARPA, decided to close. DARPA is the same agency that helped create the early internet, that funded self-driving car research decades before Silicon Valley cared, and that has quietly shaped nearly every wave of computing before the rest of the world noticed. In 2024, DARPA launched something called the Quantum Benchmarking Initiative, or QBI. On the surface, it sounds bureaucratic. In practice, it might be the most important quantum computing project in the world right now because its entire purpose is to answer the one question the industry has spent 20 years avoiding. Can any of this actually be built? And can it actually be useful on a timeline anyone should care about? The program is run out of DARPA's Microsystems Technology Office, and the man overseeing it, Joe Alta-Peter, has spent more than 15 years studying quantum computing. He's not a hype man. He's not trying to sell anyone a stock. His job, as he has described it, comes down to two brutally simple questions. First, if someone actually built a working industrially useful quantum computer, what industry would it transform? And second, is anyone actually close to doing that? Alta-Peter has been blunt about the fact that this could go either way. There is no guarantee quantum computing pans out. That kind of honesty is rare in a field this hyped, and it is exactly why DARPA's involvement matters so much. This is not a company trying to pump its own valuation. This is the United States government trying to figure out, with real rigor, whether an entire technological revolution is actually coming, or whether it is an elaborate, expensive illusion. Here is how the test actually works. Companies apply to participate in QBI, and if selected, they move through a series of stages, each one harder than the last. Stage A requires a company to describe, in detail, what a truly useful quantum computer built on their approach would look like, and to lay out a credible path to building it in the near term. Useful here has a very specific meaning. It does not mean a lab demonstration. It does not mean solving a contrived math problem faster than a classical computer, which is a trick quantum computers have already pulled off in narrow, mostly academic settings. It means what DARPA calls utility scale, a system whose computational value to the real world exceeds the cost of building and running it. In other words, a machine that pays for itself by doing something genuinely useful that nothing else can do. Companies that make it through Stage A move to Stage B, where DARPA's own technical experts, along with independent evaluators, start digging into the actual engineering. This is not a company self-reporting its own progress. This is third-party verification, the kind of rigorous outside benchmarking that has been almost entirely absent from the quantum computing industry until now. If a company survives that stage, it moves to Stage C, the final phase, where the goal is full verification and validation that an industrially useful quantum computer can actually be built and operated as intended. The target year for that milestone, according to DARPA, is 2033. Think about the timeline for a second. That is not some vague, distant quantum computing will change the world eventually prediction. That is a hard date, set by a defense research agency that does not have a habit of throwing around empty promises. And the list of companies chasing that target reads like a who's who of the entire industry. The initial cohort that DARPA selected in April 2025 included 15 companies, spanning wildly different technical approaches to building a quantum computer, because there is not just one way to do this. There are superconducting qubits, the approach used by companies like IBM and Google, which is currently the fastest industrializing path, and uses tiny circuits cooled to near absolute zero. There are trapped ion systems, championed by companies like IonQ and Quantinuum, which use individual charged atoms suspended and controlled with lasers. There are neutral atom systems, photonic systems, silicon-based systems, and more, each with its own trade-offs in speed, error rates, and scalability. By the fall of 2025, the list of companies moving forward had grown and shifted. Quantinuum, which builds what it describes as the most powerful trapped ion quantum computer in the world, was selected to advance. So was Google Quantum AI, whose Sycamore processor made headlines back in 2019 with a so-called quantum supremacy demonstration that critics dismissed as more symbolic than practical. DARPA's selection of Google for this benchmarking process signals something important. The agency believes Google has moved beyond party tricks and proof-of-concept stunts towards something with genuine potential utility. Microsoft and PsiQuantum entered a related parallel track called US2QC, which shares the same technical finish line as DARPA's Stage C. By November 2025, 11 companies had advanced to Stage B of the main QBI program, including IBM, IonQ, Quantinuum, Atom Computing, Dirac, Nord Quantique, Photonic, Quantum Motion, Quera Computing, Silicon Quantum Computing, and Xanadu. And by 2026, DARPA had launched an entirely new round, selecting 18 additional companies into a fresh Stage A, expanding the pool of contenders even further. It is worth pausing on just how different these approaches really are from one another, because the differences are not academic. They are the entire reason DARPA needs a benchmarking program in the first place, instead of simply picking a winner today. Superconducting qubits, the kind Google and IBM favor, rely on tiny loops of metal cooled to temperatures colder than deep space, close to absolute zero, where quantum effects become stable enough to control. That approach currently scales the fastest and has attracted the most industrial investment, but it also demands enormous, expensive cooling infrastructure that becomes harder to manage as systems grow larger. Trapped ion systems, the approach behind Quantinuum and IonQ, use individual atoms suspended in electromagnetic fields and manipulated with precisely tuned lasers. These systems tend to have lower error rates and longer-lasting quantum states, which sounds like a clear advantage, but they have historically been slower to scale up to large numbers of qubits. Neutral atom systems, championed by companies like Quera and Atom Computing, use lasers to arrange and control atoms that are not electrically charged, offering a different set of trade-offs between scalability and control precision. Photonic approaches, like the one PsiQuantum is betting on, try to encode quantum information in particles of light itself, aiming to sidestep some of the cooling and control challenges the other approaches face at the cost of their own unique engineering hurdles. None of these approaches has definitively proven itself superior, and that uncertainty is precisely the fog DARPA's benchmarking initiative is trying to cut through with hard data instead of guesswork. This is not a competition in the traditional sense, and DARPA has been explicit about that. The point is not to crown a single winner. The point is to map the entire landscape, to figure out which approaches have a real physically grounded shot at reaching utility-scale performance, and which ones are dead ends dressed up in impressive marketing language. As Altpeter himself has put it, there's no reason to believe the systems that even the eventual winning company has today will look anything like what they need 10 or 20 years from now. DARPA is not betting on a single horse. It is trying to understand the entire race from the inside, with access most outside analysts simply do not have. Now, here's where the story gets genuinely strange, because at the exact moment DARPA was quietly building this rigorous, methodical benchmarking apparatus, the most powerful man in the semiconductor industry was publicly torching the entire quantum computing sector with a single sentence. In January 2025, at CES, the massive consumer electronics show in Las Vegas, Nvidia CEO Jensen Huang was asked about quantum computing during a session with financial analysts. Huang, whose company had just become one of the most valuable in the world on the back of the artificial intelligence boom, said that he believed truly useful, practical quantum computers were still somewhere between 15 and 30 years away. He explained his reasoning in technical terms. Quantum computers, he said, need something like a million-fold improvement in error correction and scale before they become genuinely useful, and that kind of leap does not happen overnight. It was a reasonable, technically grounded opinion from one of the most respected voices in computing. It was also a market-moving bomb. Within hours, publicly traded quantum computing companies saw their stock prices collapse. Some fell by 30, 40, even nearly 50% in a matter of days. Investors who had piled into the quantum hype cycle over the previous year watched a huge chunk of their paper gains evaporate because the CEO of Nvidia, a company that makes graphics processors, not quantum computers, had offered a skeptical timeline in an off-the-cuff answer to an analyst's question. Shares of companies like Rigetti, IonQ, and D-Wave, which had been riding a wave of enthusiasm following Google's own high-profile Willow chip announcement just weeks earlier, fell by roughly 36 to 45% in the days that followed, wiping out a huge share of the sector's total market value almost overnight. It was a stark demonstration of just how fragile investor confidence in this technology still was, and just how much weight a single sentence from one of the most powerful executives in the world could carry. What makes this moment so remarkable is what Huang said about it afterward. Months later, in March 2025, at NVIDIA's own developer conference, the company hosted something it called Quantum Day. Huang opened the event by essentially inviting the entire quantum computing industry onto his stage to explain why he had been wrong. This is the first event in history where a company CEO invites all of the guests to explain why he was wrong, Huang said, half joking, describing the session as a kind of public therapy for himself. He later admitted, with apparent genuine surprise, that when he made his January comments, he had no idea so many quantum computing companies were publicly traded. "I didn't know they were public," he reportedly said. "How could a quantum computer company be public? I discovered they were public companies. I'm very happy for them." It was a strange, almost disarming moment of candor from a man whose words move markets worth hundreds of billions of dollars. But the story did not stop at an apology. Over the following months, Huang's position did not just soften, it reversed almost entirely. In June 2025, speaking at Nvidia's GTC conference in Paris, Huang declared that quantum computing was reaching an inflection point. He said the industry was within reach of applying quantum computers to solve genuinely interesting real-world problems within the coming years, not decades. At that same event, Nvidia unveiled CUDA-Q, a software platform explicitly designed to bridge quantum and classical computing systems, letting researchers and companies start blending the two approaches together right now, rather than waiting for some distant quantum-only future. Then, in October 2025, Nvidia went even further. At its GTC conference in Washington, D.C., the company launched something called NVQLink, an interconnect system designed to physically and technically tie quantum processing units from quantum hardware makers directly into Nvidia's GPU supercomputers. This was not a symbolic gesture. NVQLink launched with support from 17 different quantum hardware vendors and 5 controller building companies, and it was built to connect with supercomputers across 9 different United States national laboratories, under the direction of the Department of Energy. Huang called it the Rosetta Stone connecting quantum and classical supercomputers, language that positions quantum computing not as a replacement for the AI infrastructure Nvidia has built its empire on, but as a powerful new extension of it. In the near future, Huang said at the launch, every Nvidia GPU scientific supercomputer will be hybrid, tightly coupled with quantum processors to expand what is possible with computing. The U.S. Secretary of Energy at the time even weighed in, framing the project as essential to maintaining American leadership in high-performance computing. So, in the span of about 14 months, Jensen Huang went from a man whose comments crashed the entire quantum computing stock sector to the architect of a piece of national infrastructure explicitly designed to fuse quantum computing with the AI supercomputers that power the current technological boom. That is not a minor shift in tone. That is one of the fastest and most consequential public reversals in modern technology history, and it happened almost entirely in public view, one conference keynote at a time. Why does this matter so much? Because of who Jensen Huang is and what Nvidia represents. Nvidia does not build quantum computers. It builds the graphics processing units, the GPUs that power almost every major artificial intelligence system on the planet, from the large language models you might talk to every day, to the systems training the next generation of robotics and scientific research. When the CEO of that company says quantum computing is still decades away, it sends a signal to every engineer, every investor, and every government official that the technology is not yet worth serious near-term attention. When that same CEO reverses course and starts building physical infrastructure to connect quantum processors to AI supercomputers inside national laboratories, it sends the opposite signal loudly to the entire industry. Nvidia does not tend to build multi-vendor global infrastructure projects on a whim. The fact that 17 different quantum hardware companies signed onto NVQLink suggests that whatever private conversations were happening inside Nvidia and across the quantum industry through 2025, a real strategic bet was being made. And that brings the story back to DARPA, because the two threads are more connected than they might first appear. DARPA's quantum benchmarking initiative exists precisely because moments like Huang's January 2025 comments expose a deep, uncomfortable truth about quantum computing. Nobody outside a small circle of specialists actually knows, with confidence, how close this technology really is. Public statements from CEOs can swing billions of dollars in market value overnight, based on little more than an educated guess offered in a 5-minute answer to an analyst's question. That is an unstable, almost absurd way for an entire technological revolution to be evaluated. DARPA's answer to that instability is rigor. Instead of asking a CEO for his gut feeling, DARPA is putting dozens of companies through multi-year, independently verified technical benchmarking, stage by stage, to build a real, evidence-based picture of where this technology actually stands, separate from hype, separate from stock prices, separate from any single person's public mood on a given day in Las Vegas. It is also worth noting that DARPA's involvement in quantum research did not begin with this initiative. The agency has a long history in the field, stretching back more than 2 decades. including an early quantum key distribution network built in the early 2000s that connected optical nodes across Boston and Cambridge, Massachusetts, and ran continuously for years as one of the first real-world tests of quantum-secured communication. That history matters because it shows DARPA is not chasing a passing trend. It has been quietly funding and studying quantum technology since long before Wall Street or Silicon Valley took much notice, and the Quantum Benchmarking Initiative is best understood as the natural, more mature evolution of decades of patient, largely unpublicized government research, finally meeting a moment where the underlying engineering might actually be ready to deliver. There's also a national security dimension here that should not be overlooked, and it is a big part of why DARPA, a defense agency, is the one running this program in the first place. A sufficiently powerful quantum computer could, in theory, break many of the encryption systems that currently protect global communications, financial transactions, and classified government information. That possibility alone is enough to justify enormous government interest in understanding exactly how close the technology is, and it is one reason DARPA has separately been involved in evaluating claims about quantum computing's potential impact on military encryption. At the same time, DARPA officials have described a broader shift happening inside the agency, moving quantum research from the realm of pure science into applied engineering that can actually be deployed on real platforms in real operational environments. That shift mirrors almost exactly what has been happening in the commercial world, with companies like Google, IBM, and Quantinuum. The science phase is ending. The engineering phase, the one where things either work at scale or they do not, is beginning. Skeptics remain. They are worth taking seriously because hype cycles have burned investors and researchers before. Some of the same experts who have watched quantum computing promises come and go for 20 years point out that today's systems still require extreme refrigerator-defying cooling, still struggle with high error rates that make complex calculations unreliable, and still need to scale from hundreds of qubits to potentially many thousands before the kind of transformational use cases people imagine become real. Huang's own January 2025 comments were not baseless. They reflected a genuine, widely shared concern among people who understand the underlying physics. Getting from where quantum computing is today to where it needs to be requires overcoming some of the hardest engineering problems in the history of computing. His reversal does not erase that difficulty. It simply reflects a shift in how close he now believes the industry is to clearing those hurdles, driven by real technical progress from companies racing through DARPA's benchmarking gauntlet and beyond. That tension between genuine skepticism and genuine acceleration is exactly why DARPA's Quantum Benchmarking Initiative matters so much right now. It is not designed to settle the debate with a press release or a keynote soundbite. It is designed to settle it with years of independently verified engineering data, company by company, approach by approach, milestone by milestone, all pointing toward that 2033 target. If even a handful of the companies currently working through Stage B and the newer Stage A cohort succeed in proving they can reach utility-scale performance, the implications reach far beyond stock prices. Fields like drug discovery, where simulating molecular interactions is currently limited by classical computing power, could see breakthroughs that take years off the development of new medicines. Material science, the search for better batteries, stronger alloys, more efficient solar cells, could accelerate dramatically. Optimization problems that currently take classical supercomputers days or weeks, the kind used in logistics, finance, and energy grid management, could potentially be solved in a fraction of the time. And artificial intelligence itself, the very technology Nvidia has built its empire on, could gain an entirely new computational substrate to build on top of, rather than being replaced by it. That last point is worth sitting with, because it cuts against a common misunderstanding. The story here is not that quantum computing is coming to replace artificial intelligence, or that one technology is about to eclipse the other. Nothing DARPA has said, and nothing Jensen Huang has said, supports that framing. What both DARPA's benchmarking work and Nvidia's NVQLink infrastructure actually point toward is convergence, not competition. The vision Huang laid out at NVQLink's launch was explicitly hybrid. GPU supercomputers tightly coupled with quantum processors working together, each handling the parts of a problem they are naturally suited for. Quantum computers are not expected to replace classical computers or AI systems anytime soon, if ever, for most everyday tasks. They are expected to serve as specialized accelerators for a narrow but extremely valuable set of problems that classical and even AI-driven systems currently cannot solve efficiently. That is a very different story than the ones that tend to go viral online, but it is the story the actual evidence supports. So where does that leave us, heading toward 2033? DARPA's Quantum Benchmarking Initiative will continue moving companies through its stages, with more rigorous, independently verified data becoming public as milestones are reached or missed. Nvidia will continue building out NVQLink and CUDA-Q, expanding the bridge between classical AI infrastructure and quantum hardware across national laboratories, and eventually, likely, commercial data centers. Companies like IBM, Google, IonQ, Quantinuum, and dozens of others will keep racing to prove their particular approach, whether superconducting, trapped ion, neutral atom, or something else entirely, is the one that actually scales. And somewhere in the middle of all of it, a defense research agency that has spent decades quietly shaping the future of computing will keep asking the same two unglamorous essential questions it started with. If this actually works, what does it transform? And is anyone actually close to making it work? Nobody, not Jensen Huang, not DARPA, not the companies pouring billions of dollars into this bet, can promise you a guaranteed answer today. What has changed dramatically and verifiably over the past 18 months is the confidence of the people closest to the problem. A CEO who once said useful quantum computers were decades away is now building physical infrastructure to fuse them with the AI systems that define this era of technology. A defense agency that started by asking whether any of this was real is now running dozens of companies through the most rigorous public benchmarking process the industry has ever seen. And a target date, 2033, sits on the calendar as something closer to a deadline than a dream. It is also worth remembering that this entire conversation is unfolding against the backdrop of an industry that has kept delivering incremental, real technical progress, even while the public debate swung wildly between hype and doubt. Throughout 2025 and into 2026, companies pushed forward with genuine milestones that rarely made it past specialist publications into mainstream headlines. Quantinuum launched a new system it called Helios, which it described as the most accurate commercial quantum computer available at the time, aimed squarely at proving that trapped ion architecture could deliver reliability at a scale enterprises could actually use. Google continued refining its superconducting approach, following the attention generated by its Willow chip. IonQ kept expanding partnerships with research institutions and government labs, including collaborative work referenced alongside DARPA's own benchmarking efforts. None of these individual milestones, on their own, proves the industry has solved quantum computing. But taken together, they paint a picture of steady, unglamorous engineering progress happening underneath the noisier public narrative of stock crashes and CEO reversals. And that quieter progress is arguably the more important story for anyone trying to understand where this technology actually stands. Whether that deadline gets met is still an open question, and anyone who tells you otherwise, in either direction, is probably selling you something. But the direction of travel, from skepticism to serious, well-funded, technically grounded investment, from vague promises to hard, verifiable benchmarks, is no longer in doubt. Quantum computing spent 20 years as a technology that was always almost here. For the first time, thanks to the combination of rigorous government evaluation and serious private infrastructure investment, there's a real, dated answer on the horizon. The next few years will determine whether 2033 becomes the year quantum computing finally arrives, or one more milestone the industry quietly slides past. Either way, the test is already underway. And this time, for once, nobody is just taking someone's word for it. Not a CEO's word, not a headline, not a stock chart moving on a rumor. Just years of patient, independently verified engineering, company by company, milestone by milestone, counting down toward a date the whole world will eventually be able to check for itself, out in the open, with the receipts to back it up.